Hi, everyone, and welcome to today's Colloquium talk. We have Brian Johnson here today from the University of Washington ECE Department. Brian is the Washington Research Foundation Innovation Assistant Professor in ECE, and his research area is power electronics. He obtained the master's and PhD degrees in electrical and computer engineering from UWECE in 2013. And then he was a research engineer with the National Renewable Energy Laboratory in Colorado. He was awarded a National Science Foundation Graduate Research Fellowship and serves as an associate editor for the IEEE Transactions on Energy Conversion. So thank you very much, Brian, for speaking to us, and welcome.
Thanks for the intro. Okay, so today I'll be describing a line of work that actually stretches back around 4 or 5 years, and much the way this works is, you do research and different things pop out of it, and we had 2 disparate pieces that it turns out looked different, and we're able to tie them together and realize that there's actually kind of a unified way to look at things. And so that's just kind of a nice story on how this this line of work that I'm talking about today came together. Okay, so this work, because it encompasses theoretical aspects, hardware, and many different things, there was actually a lot of individuals that contributed to this. So here's a list of some of the main people that I worked with on this. Now, I do understand that this audience has a pretty wide variety of backgrounds amongst the people in the audience. So I want to give everyone here an intro to power electronics. And okay, let's see here. Oh, all right. I just jiggle cores. That's how I debug things. Okay, so what I want to do is I want to give everyone a Power Electronics 101 real quick, just to set the stage for the rest of the talk. Okay, so the main idea of power electronics is that it's circuitry that is meant to move energy from point A to B, where point A and B can be almost anything. This could be a battery in your phone and a processor in your mobile device, to a wind turbine in the grid. It's really just everywhere. Now, if you look at the way power electronics are built up, the key ingredients are power semiconductors. So here I drew a diode and a MOSFET, for instance. And these are actually modulated so that they act like ideal switches. And if you think about an ideal switch, when it's closed, there's no losses through it, has 0 resistance, and when it's open, no current flows, so there's 0 losses. And then if you look at inductors and capacitors, same thing. These only store energy, and they do not lose energy. So ideally, if you use these ingredients, you can build highly efficient circuits to move energy around. And here's just a couple quick examples. So this here on the bottom left is called a buck converter, which is just meant to step down one higher DC voltage down to another one. And you can just think about it like this. Let's say you have a voltage Vn, and if you have 2 switches that you operate in a complementary fashion, then you end up with this kind of sliced up waveform here. And then these LC circuit elements on the output just filter out these high frequency components, and you recover a lower voltage. And because of these ingredients here, it should be highly efficient. This kind of converter is ubiquitous. It could be in all your computing devices and in many different applications. Now here's one circuit here on the bottom right that converts DC to AC. So here, let's say you have a DC voltage. Now things are a little more complex. Here's 4 switches, and those extra 2 switches allow you to create a switched waveform that goes positive and negative. And again, if you filter that out, you can get an AC waveform on the output. So this is a DC to AC converter or an inverter. And so there you go. This is the background on power electronics. These are the 2 main circuits we'll actually be talking about in our discussion today. There's some key characteristics we need to look at. So if you look at the waveforms inside of these converters, so let's go back to that step-down buck converter. So here we have this kind of discontinuous sliced up voltage waveform. Now, one thing that's really important is to actually look at the currents that flow in these kinds of circuits. Now, because the voltage across this inductor is continually going between a high value and a low value, the current actually looks like a piecewise linear triangular waveform when you zoom in very close at this high switching frequency. Just so you know, these switch generally, it could be anywhere from kilohertz to megahertz. But when you zoom in at that switching frequency, you see this, this rise and fall, and it's called ripple. And the other feature that we need to be cognizant of is you have to control these things. So these are just semiconductor devices. They're not smart. They're really dumb. So we need to add controls around it so that we can manipulate them to do what we want. And so the way that works is, at least if you do it with digital control, I know there's a lot of embedded systems students here. So here you can measure voltages and currents, convert that into a number, and then here you have a control loop that is manipulating the switching action of these two switches, where you can either regulate voltage or current, or potentially both. So there's a lot of algorithmic flexibility on how you can program these controllers. Okay, there you go. So you all have a background now in power electronics, and you can move forward with that knowledge. And here is the bigger picture context of what we're going to be talking about. So when I talk about modular power electronic systems, this just means that we're looking to assemble larger systems out of many smaller pieces. So for instance, if you have a PV array, each one of these PV modules could have a small power converter on the back of it. So that is one example of a modular system. Renewable systems also tend to be modular. You have one renewable energy conversion interface, and you can take many copies of that. And then even if you look at computation, so here you need many power converters to process the energy, let's say in a data center. So if you have this modular structure, there's a lot of really great benefits you can get from that. You can simplify installation. If you do things correctly, hopefully it's plug and play. You just kind of snap these pieces in like Legos and it all just works. You can expand the system. And if you also play your cards right, you can get a lot of resiliency too. So if one of these power converters or these modules fails, then the other units can continue humming along. Okay, so let's take a closer look at what you have to do in these modular systems. It really just depends on the application, but there's two key objectives I want to look at. The first one I want to discuss is what I call the synchronization problem. And this is the idea that, let's suppose that you have a bunch of DC to AC converters, and you want to have them work together in an installation. Now, if each one of them is producing a sinusoidal waveform, they all need to do that together as one unit. So they need to synchronize with each other. And so that is a key objective that we have to be mindful of when we are assembling AC systems with many power converters all working together. All right, let's switch gears a little. So here's the AC case. Now let's look at DC. Now DC is a bit different. And this is, again, going back to what I described earlier. There is this switching ripple, which is undesirable. It's a distortion. And generally, if you're supplying power to a load, you don't want to inject distortion into that load. So there's a clever trick that was invented a while back. It actually goes back to, I think, the early 90s, which is called switch interleaving. So you can imagine here that if each one of these power converters is switching and has a switching frequency, if you were to evenly space out the phases of the switch timing of each of those, that means that each one of these little ripple waveforms is slightly offset from one another. And due to just Kirchhoff's current law, when all those currents sum up, those ripple distorted components that you don't want can just cancel out. So that's a really nice, elegant approach for canceling out this distortion without resorting to large, bulky filtering elements. You just let KCL do the work for you. Okay, so if you just look at these two cases side by side, they almost have this opposite and different nature to them. So in the AC case, we want things to move together as one. And then in the DC case, we want them to kind of do anti-synchronization, which I call interleaving. And some people in the control systems world call this splay. So here we have this kind of opposite or dual nature of these two systems. And like I kind of hinted at earlier, we're looking at these two problems in kind of an independent way and realize that what's surprising is you can actually use the same controller. It's just recycled in a different way. And you can do it for both the DC case and AC case, where all you have to do is you have to just flip the sign on the feedback of how you feed the measurement into this control unit. And let's say this is a DC to DC converter or a DC to AC converter. In one case, if you have this negative sign on this feedback, then you'll get synchronization. And if you have a positive sign, then you'll get this interleaving. So anyway, that should hopefully be a little bit surprising to you, and we'll work through the mechanics to show you how this is actually true and how it's done. All right, so I like to try and please everyone I can in the audience. I know there's a lot of people here that have varied interests, so there should be something here for you. So on the application side, here we'll be talking about all the hardware and experiments, and we'll do that first. Just so you know that this is not crazy stuff I'm just making up. It's real, we built it, it works. If you're more of a mathematically inclined person and you want to see why it works, then we also have the modeling aspect to show you how we study the behavior of these systems. And then finally, we'll even take the math up to another level and show how we get stability. So here we actually pose the problem of synchronization and interleaving as different types of stability problems that we study. Okay, so let's begin by taking a look at the hardware and seeing the various things that have been built up over the past several years. All right, so the first thing we'll look at is the AC case, and we'll look at this synchronization problem. All right, so here I'll just come right out and show you how this control structure looks like for one single DC to AC converter. And remember, I'm talking about modular systems, so in just a second I'll show you how we take multiple copies of what's on this slide and build up complex systems out of them and have them synchronize with each other. Okay, so this is the individual unit. The bottom part of the diagram is the power electronics. So this is the actual power hardware that moves energy from point A to B. You can think about this as being really the workhorse, the beefy part of the system that has to move energy around. And then everything in this blue box is the embedded system. So there's the digital controls that live inside this blue box. So here I've drawn what's happening inside the controller as it looks like it has a circuit element and all these lines feeding in there, but it's really nothing more than just lines of code running in real time. So just let me just walk you through how it works. So on the real physical side here, we have actual voltages and currents. We have analog to digital converters that convert that into numbers that are read into a DSP or an FPGA, for instance. And then we feed that into this virtual oscillator controller, as I call it. Now here I've drawn it as an actual circuit, but in reality, this is we're just taking the differential equations associated with this circuit, we're discretizing them, and then we're just programming them inside of the embedded controller. Another way to look at it is inside this controller, we're emulating this circuit in real time, so it's kind of fictitious, and this is why we use the word virtual to describe this oscillator circuit. And then finally, we get this fake voltage across this oscillator that we're emulating, and it turns out that we can control the switching action on the physical converter such that this voltage here that's at the terminals actually follows the voltage that's produced by the oscillator. So if you look at this closed loop structure here, you have physics. It's fed into the system reacts, and then the system is producing a physical voltage. So it is a closed loop system, and what's neat here is that this fictitious oscillator behaves as if it's interacting with the real system because of this closed loop behavior. Okay, now one thing I want to do here is this circuit here has a resonant structure in it. So if you're looking at this and you see this LC tank, it has this resonant frequency. which is 1 over the square root of LC. And now we're going to pick that resonant frequency to coincide with the frequency of the AC waveform we want to produce. So let's say we have a 60 hertz grid. This can be tuned for resonance at 60 hertz. And then here's this feedback sign. Remember, this is the thing I'm going to say. We can just flip the sign on this to get different behaviors. So in this case, this is a negative number. OK, so we have multiple copies of this now. So now we're going to take a bunch of instances of what I just showed you on the previous slide and build up a system with many of these connected all in parallel with each other. Here's a picture of something that we actually built up. So everything in this red box is the power electronics. You can see it's bigger and physically larger, has to move energy around. And then this has a little DSP on this control card that's sitting separately. All right, so let's look at some waveforms here. OK, so here is an experiment where we have 3 of these power converters. Our inverters are producing AC on the outputs. We connect them across a load. And this here is this virtual oscillator controller, which I call VOC. We actually, there's a bunch of details here that don't have time to talk about, but we actually have ways of designing the individual unit so that that single unit knows what its power rating is. And when you connect them in a system, they can all share power in proportion to their own power rating. And they can do it without communication. It may seem very magical. How are these things synchronizing with each other? So here, we start them up. The other ones don't explicitly know the other ones exist. They just synchronize, and then they share power in proportion to their rating. So it all seems magical, but it's not. Really what makes it work is it's Kirchhoff's laws. They talk to each other through the physics of the system. So the conductors give rise to networked interactions, and then we have the feedback loop. And it turns out that if you analyze this very carefully, that's how they synchronize. And they do it by just leveraging the network itself. OK, so here is just showing an experiment where we have a load step. And you can see that they provide a nice consistent voltage in green. And they just give the load whatever it wants. And they share this burden proportionally. So that's pretty cool. So there you go. You have a load. You can just put a bunch of these in parallel across that load. And they'll provide reliable power to that system. OK, here's just another quick experiment where we put a more realistic load. This actually looks like something you might see on the front end of like a computer power supply or something like that. So this has a rectifier. Real loads have all sorts of gnarly currents that they draw. So this is an experiment just to show people that you can power realistic things with these. And here I'm turning off a unit. Oh, sorry about that. Here I'm turning off a unit. You can see the others step up, and then here I bring it back and continue working. OK, there's another backstory to this, too. It turns out that there's controllers that have been known to give you this AC side power sharing and synchronization without communication. There's something called droop control. It's been around since the early 90s. And this controller is actually considerably faster and more nimble, higher performance. So here is actually the same experiment run twice with this, you can say this old school controller that everyone has seen before, at least in the power electronics world, and then this new controller. And we actually verified that we can get a pretty good gain in terms of the performance. OK, so now let's switch gears to the DC case. And now we're going to look at the step-down buck converters. All right, so here, this is another experiment where here you have a DC voltage source that is powering a DC load on the right-hand side here. And this modular structure, we have a bunch of parallel buck converters in parallel with each other. This is actually very similar to what you would see in a CPU power supply. So if I were to tear open my laptop and look at the power supply, this would actually be called what's referred to as a multi-phase buck converter, where they refer to the multi-phases being the fact they have multiple buck converters all in parallel with each other, serving that computational load. So this is just a abstraction of what that computational load would be consuming. Now, the conventional way this is done is you usually have a centralized controller, but we wanted to do this in a completely communication-free, modular way so that you can just plug all these in and they'll do this interleaving and ripple cancellation without communication. So this blue box is the new controller that we developed. Again, you can see there's this commonality from what I showed you before. So we have this fictitious oscillator that lives inside of it. Here's this feedback gain. I said that we're going to flip the sign now. So whereas before it was negative, now it is positive. So that's one of the key differences. And the other key difference too is whereas before we tuned the resonance of this circuit to coincide with the AC waveform frequency you want to produce, let's say for a 60 hertz AC grid. In this case, we tune it for resonance at the switching frequency. So we want to interleave them at that switching frequency, so we are tuning their behavior to react to that frequency. In other words, the resonant frequency is a way of picking where you want it to take control action at. Okay, so here is the experiments. So here is 5 buck converters. They each have their own FPGA. And here is the experiment we built up. Here's just a quick backstory too. The first time we wrote a paper on this idea, it was just pure simulation. And people said to us, I don't believe it. It's not going to work. This is crazy talk. I don't know what you're saying here. And actually, one of the key things someone said here is, they said, this is a very highly symmetric setup we're simulating here. And they wanted to know what happens if you have resistances that separate them. Imagine you have a long bus bar and you have converters hanging off of them. You might actually have impedances between them. Well, one of my favorite things to do in life is whenever I hear someone say something is impossible, I like to disprove them. So that's exactly what we set out to do. So we built the experiment. We added these resistances that other people thought would just wreck this thing. And we ran the experiment. And lo and behold, you can probably guess, it actually works pretty well. So here is the experiment where here I'm showing the total current that flows into the load. So let me just back up. This is the total current going into that, let's say a computational load, for instance. And then these are the individual currents. We're zooming in, and here is that triangular ripple I was talking about. So we actually start them out completely random. They don't know that they exist. All the other units exist. And actually, you can see here that within a few milliseconds, they all kind of push each other apart. And here you get this interleaved or splay behavior that I was talking about. So here, you can actually see that we obtained what we were looking for. The other thing, again, we want to show this plug-and-play behavior. So let's say you have a system that starts out with 4 units up here. They're each 90 degrees spaced apart. And then let's say at some point I turn on the 5th unit here. Then again, the 4 don't know that one turned on, but it's just through the physics and the feedback, they all kind of push each other apart. Okay, so just real quick on the larger context and where this fits in terms of what's been done historically. So for past couple decades, the way this is always done is this centralized method I'm showing on the far right is by far the most ubiquitous way to do it, even today. If you look at the semiconductor manufacturers that make chips that manage these things, this is the way it's done. There's some recent work in the academic world where you use communication buses to kind of spread out these things, but as far as I know, in industry that hasn't been done. And then this is our breakthrough here. This is something that's the first fully decentralized way of doing this interleaving approach. Okay, so that concludes all the experimental aspects. And so the next thing I'll do here is to show you that this is not magic. You can actually apply mathematical methods to uncover what is actually happening here and see what's going on. Okay, so the common underlying kernel and main ingredient of all of these is this oscillator structure. As you saw, I was just repeating it and using it over and over. So it is worth looking at its structure a little bit more closely. So this circuit has dynamics that you can describe by this differential equation. where y and x can be thought of as just being scaled versions of the capacitor voltage. So in fact, y is that capacitor voltage that's here, or across this capacitor. X is just a scaled version of the current that flows through this inductor. And when you write things in this form, where this epsilon value is just the characteristic impedance of this LC tank, so square root of L over C, you can write things in this very nice format where this first term actually is the equation for the harmonic oscillator. So you see physics 101, a frictionless pendulum, that's the same equation that gives you this first term. The second term captures the behavior of this nonlinear piece. And then this third term captures the fact that you're coupling it to a network. So this is where the interactions with the rest of the units give a rise in this model. Now, if you initialize this with 0 input, meaning that there is no current here, it's an open circuit, and you turn it on, then this thing has this limit cycle. So limit cycle is just saying it's a fancy word for a periodic oscillation here. And it looks like a sinusoid. It's actually not a perfect sinusoid, but it's very close. And you can actually pick all the parameters like this resistor, this alpha parameter, and so on and so forth to give you a prescribed amplitude. And here you can see that it converges to this desired limit cycle in polar coordinates. So here's the time domain on the x-axis. This is showing how things look on polar coordinates where the x and y axes are these, the capacitor voltage and scale inductor current, and it reaches this periodic circular orbit. Okay, so that's a single unit. And we have to couple this together in a network. And here we have to use a little bit of imagination because I want to study the DC to DC case as well as the DC to AC case with the same kind of model. And I want to be able to just flip the sign on this kappa I, which is that current feedback, and study what's going on. So the main idea here is that we want to kind of abstract away the differences and just retain the commonalities between those two applications I showed. So the feedback is very similar, has the same form. And this model captures the behavior at this nominal frequency, this omega star. So omega star is just capturing what is happening in that given system at the resonant frequency. So omega star in the AC case was, let's say, the grid frequency, 60 hertz, 50 hertz, whatever. And in the DC to DC case, omega star was the switching frequency. But other than that, it's the same exact model for both of them. And we assume that there's multiple copies of them interacting with each other through the network. And the network interactions can be just given by this equation. So I here is the vector of all of the currents that are being injected into those oscillators. VC is the vector of all of these capacitor voltages. And Y is a square matrix that tells you what the network structure looks like. Okay, so now we're going to work to define the angles. And here it's convenient to look at angles because, remember, we want to look at the timing of these. In one case, we want everything to be aligned. In other case, we want things pushed away. And the nearly circular orbit of these oscillators allows us to define this angle straightforwardly. So for this kth oscillator, you can take the ratio of that capacitor voltage and that scaled inductor current and take the arctan of that, and that gives you an angle. And this is just like going back to that polar plot where I showed this thing is making a circular rotation. Now, one thing I do here is I subtract off the nominal frequency times t. So this actually gives you, you can say, if this green dot is spinning around, this gives you the rate at which it spins nominally. And then this other term gives you, I guess, the offset with respect to that. It's also pretty easy to define an amplitude. So this radius r is just the square root of the capacitor voltage squared and then the scaled inductor current squared. All right, so now this is where things get a little messy here. So we have a network here. So all of these things interact with each other. So it's just Kirchhoff's current laws that give you all the currents and voltages. So here, if you go back to the network and you look at this I equals y times v expression I gave, and you substitute that in, and you work through all the trig and look at what is the differential equation for the angular dynamics and the radii, you end up with this equation. All right, so it's not too pretty, but it is what it is. So one thing we do to simplify analysis, because that equation I just showed on the previous slide is fairly difficult to work with, is we actually average out the dynamics over one cycle. So if you actually look at the periodic orbit of one of these going in a circle, it actually has a slight wobble to it, but it's almost a perfect circle. So when we do this cycle average over one periodic circular orbit, we kind of are neglecting that little wobble, which really doesn't do much. So the average dynamics looks like this. So this r hat dot is telling you what is the averaged amplitude of it as it makes one circular excursion. And this is the averaged angular dynamics over that system. And here, just notation-wise, this theta jk is just a shorthand way of just saying we're looking at angle differences. Okay, so this equation here is much simpler to work with, and there's some really beautiful properties that it has and allows us to start studying the system more carefully. Okay, so like I said, timing is everything. We want to look at how these things either sync up with each other or push each other away. So we're going to look at these three different cases. So the first one is the phase synchronized case, where everything kind of oscillates and moves as one. This is the AC case. And then there is another condition that we call the phase balanced case. So you can imagine that if all of these things are spinning around in a circle, and they all are kind of more or less evenly spaced out around that circular torus, this is called the phase balanced case. And this is a fairly general condition. Now, if you look at a very particular case, it turns out that interleaved case that I really want to obtain for the DC to DC converters is a special case of this phase balance condition, where not only are they spaced out in a more or less balanced fashion across the torus, but they're actually equally spaced out, and you can write the angles just like this. Okay, so now here comes the fun part. Now we're going to look at how we can study the stability of the synchronized condition and the interleaved case. And we're going to look at those one at a time. We're first going to look at the synchronization case, and we're going to see what's going on with that condition. So this is like, let's say, for those AC converters that are all powering a load. Okay, so here I have a theorem which sounds really scary, but it's really not too bad. So here we say that we have the N oscillators. They have the dynamics here. I haven't done anything here. I'm just restating those same diffie Qs from a couple slides back. So it's just restating it. And here is that really important feedback gain. So if that feedback gain is negative, then we have this radius equilibria here, given by this R dagger. And it turns out that all the angle differences are 0. And that condition, or that point, sorry here, let me, all right, here we go. That condition, and actually what's most important here is those angle differences being 0, is locally exponentially stable. Okay, so if you're wondering what is going on here and how does this come about, so what we do is we have these two nonlinear differential equations for the angles and the radii, and here we study and find where the equilibria occur. So we set all these dots to 0, and we solve for where the system has an equilibrium. And then we linearize around that point, and when we linearize around that point, we end up with what's called a Jacobian, and if you study that matrix, that tells you at that exact point if that system is stable. And it turns out that that operating point is stable and things tend to converge to that point. So this is a way of mathematically establishing that if you have this negative sign on the feedback, that the synchronized condition is attractive, at least close by to it. All right, so now let's go to the phase balanced case, which is the general case of the interleaved condition. And it's the same thing here. So we have another theorem. So the first part is exactly the same. Again, we still have the same r dot and theta dot. Nothing has changed. It's the same model for both systems. Now we have positive gain on that current feedback. And we do have a condition here on how the parameter, this sigma is it characterizes the resistor in that virtual oscillator. And as long as we have that condition here met, then this phase balance condition with equal radii is locally exponentially stable. So again, this just means that condition where all of the angles are spaced across this circular torus is something that's attractive at that point when we have this positive feedback. And here again, it's the same story. You can just set all these derivatives to 0, solve for the equilibrium. You look at this Jacobian, where this is a standard linearization approach, and you actually look at the diagonal blocks, this JA and JD, and you can study their properties to establish that indeed that point where everything is spaced apart equally is attractive, at least locally. Okay, so here is a summary just to show you. So the synchronized case, if you this is the first theorem I showed you. Here's theorem 2 on the far right-hand side. And if you just look at all the different possibilities where you have positive and negative gain at each given condition, you can see that the two stable operating points indeed are the synchronized case for the negative feedback, and then the interleaved case for the positive feedback. And this is how I put a bow on this past 5 years, and hopefully you enjoyed seeing how all of that came together. So I'll take questions at this point. Yes.
What happens in the interleaving case? What happens if you have a different amount of energy available from each of the sources? Does it properly interleave at different angles that are not equal?
Yeah, so in most systems, actually the diagram that, let me see if I can pull this up, just one sec. Okay, so the application we were looking at for the DC to DC case, we were really trying to target computational systems. And usually the way that's done is this VDC is the same bus. And so they're all pulling from the same bus. And I haven't really looked at where the non-uniformities on the DC side, how it impacts the system. Now, from experiments, what we have observed is that it's fairly robust, but you will get small angular offsets from the ideal interleaved case, but it's modest.
So
Yes.
did you initially intuitively perceive that they would interleave evenly? How did that idea come about?
Yeah. So that's a good question. How do these things happen? So the sequence of events is actually kind of how I presented it. We looked at the AC case first and studied the synchronization condition. And one of my collaborators, one of the people on that first slide, he was just playing with some simulations when we were working together. And he said, hey, I flipped the sign and these things push each other apart. And so we observed that and we're highly intrigued. And then the rest is the story I talked about.
Did you use an FPGA or a DSP?
For this one, with the DC to DC case, we use an FPGA, and then for the earlier ones with the AC converters, we use the DSP.
I can just keep going. The frequency that you're testing, this omega, did you think, well, we should test the frequency just less and just more, or did that ever come to it? Like, if it starts to slide off into this, one omega, delta omega to the left or to the right, we don't want it to go there. How did you, or did you just need the one omega to keep it balanced?
Okay.
Do you have to test a bunch of omegas to get it to line up to one omega?
Okay, yeah, so, oh yeah, so I should be restating questions because we're being recorded here. So the question, at least from what I perceived, is how is it that these things are able to all take behavior at this particular frequency when they all don't know of each other's existence? And how do they do this? So the reason this works is because we program them all with the same resonant frequency. So even though there's separate DSPs or FPGAs for all of them, we program them with that same resonant frequency, and then that is enough to give you this behavior.
Well, following up on that, what if the resonant frequency of your oscillator is not exactly the same as the switching frequency of your buck converters?
Right, yeah. So in that case, so the question is what if there's a mismatch between the switching frequency and the resonant behavior or resonant frequency of the tank? So what I would think would happen is that the performance would degrade. So you do want to know what your switching frequency is and then to tune that to coincide with that. But because everything in this blue box is, actually, hold on. The oscillation that is produced by this oscillator is actually one and the same with the switching frequency. So if you tune this to be resonant, it should automatically give you a switching frequency at that particular frequency. So I think in this case, we're actually protected from that problem.
How about the other case where you have the grid frequency and then your oscillator frequency?
Right, yeah. So the other system, it does also have some robustness built into it. So the question was, what about in the AC case from earlier? There is something called frequency droop that is kind of naturally embedded inside of this, which means that if the frequency on the system moves around slightly around the nominal value, then the system is still able to share power and work as a cohesive system. So I think even in that case, we have robust performance.
Great. Well, I think there'll be individual Q&A time afterwards, but let's thank Brian very much and welcome Brian to UW.
Thanks, everyone.